This robot balances for about 3 seconds. Just pure engineering. And honestly, getting here was an absolute disaster. Weeks of failure, violent crashes, and one very traumatized robot. Let's check it out. A self-balancing robot is an inverted pendulum, which means it's always falling. Our job is to catch it before it falls. Sounds easy, right? Absolutely not. To react that fast, it needs to know exactly how much it's falling, and that's where the sensors come in. This tiny board is an IMU. Inside it, a gyroscope measures angular velocity and an accelerometer measures acceleration. Individually, these sensors are useless. The gyro drifts and the accelerometer jitters, so we combine them with a sensor fusion algorithm. You can use a Kalman filter or a complementary filter, which is basically the Kalman filter's simpler, less traumatizing cousin. Since I have absolutely no idea how a Kalman filter works, we'll use the complementary one. Here's the idea. We've got two angles, but they're not equally as trustworthy. The gyroscope is usually much more reliable, so we'll decide how much of our final answer should come from it. Let's say 98%. That leaves 2% for the accelerometer. So we take 98% of the gyro angle, 2% of the accelerometer angle, add them together, and that gives us our estimate of about 5 degrees. Great, we know the angle, so let's talk about how the robot actually corrects itself. Enter the PID loop. I know, it looks super fun, but we're gonna have to make this quick for everyone's goldfish attention spans. Our microcontroller uses the discrete version of the formula, and I'm gonna run through how it works. The equation has 3 main terms, P, I, and D. P stands for proportional, and reacts to how far the robot is off balance. On its own, the robot will stand, but it'll overshoot and oscillate. To calm that, we add D for derivative. This slows the motors down as we get closer to upright. And finally, I for integral, which fixes steady state error. If the robot leans slightly for a long time, the integral term builds up and nudges it back. Still with me? Great. We can tune how strong each term is. Some typical values are 20, 0.8 and 1.2. After substituting the error values in the time step into our equation, it will output a number. That's the command for the motors. Positive spin them forward, negative spin them backwards. If we ignore the sign and take the absolute value, the size of the number tells you how hard the motors have to push. Now let's build it. First, the electronics. I opened fritzing and made an epic schematic. This helps us know where to wire everything when it comes to soldering. I've also added these little OLED displays to make the robot look super awesome. To power the motors, I use an L298N. You probably know this already, but it lets the ESP32 control the motors with only a little bit of current. Next, we have to program it. I opened Fusion 360 and made the coolest robot ever. It has shelves. Bottom shelf is for the motors, next we mount the logic board, then the OLEDs and motor driver, and for the top, the battery. If you want to build your own, but like me, you don't really understand it, or you don't want to suffer through modeling and programming, check the website. Full documentation, all files, completely free. As with all projects, it obviously didn't work. The robot immediately slams to the ground. Turns out, blindly trusting ChatGPT isn't always the best idea. It told me to put the heaviest bit, the battery, at the top. This should increase the moment of inertia, helping balancing. But in my experience, the leverage was too much for the motor to handle, so I disassembled the whole robot. And now it still doesn't balance. Remember these PID numbers from earlier? Turns out you can't just use those values. You've got to tune them manually. This only took a month. Yeah, I got a bit distracted and started on a new project. But after days of tweaking, falling over, and occasionally questioning my sanity, seeing it stand for the first time was incredibly satisfying. This random jumble of wires and plastic held together with questionable solder joints, balancing all on its own. If you want to build your own or just curious, check out the website, link in the pinned comment. Hope you learned something today, and if you did, consider liking the video, subscribing to the channel, and leaving a comment. See you in the next one.